Recently, CCTV Finance featured a report titled Superglass, a Trillion-Yuan New Track. Companies are racing to invest, spotlighting the development of the glass substrate industry. Peng Shou, an academician of the Chinese Academy of Engineering, predicted that by the end of the 15th five-year plan period, around 2030, the industrial scale formed around superglass is expected to exceed 1 trillion yuan. This has rapidly transformed glass substrates from a specialized technical term in semiconductor packaging into a hot topic for both capital markets and the materials industry. However, we need to clarify a commonly confused point. The trillion yuan level mainly refers to the broad industrial ecosystem formed by specialty glass in areas such as AI computing, 6G RF, low-altitude economy, and new energy. Rather than meaning the semiconductor glass substrate market itself is already worth trillions. What truly deserves attention is that glass is moving beyond display panels, cover glass, and optical components, further entering the core structural layers of chip packaging. What exactly is the glass substrate discussed here? The glass substrates discussed in this article primarily refer to glass core substrates, glass interposers, and TGV glass substrates used in advanced semiconductor packaging, not common display glass or photovoltaic glass. TGV stands for through glass v. IT requires processing a large number of microvias in specialty glass, typically less than 1 millimeter thick, followed by whole wall metallization, copper filling, redistribution layers, RDL, dielectric layers, singulation, and reliability verification, ultimately forming a high-density interconnect structure that connects chips, memory, and packaging substrates. From a material structure perspective, it sits between the chip and the PCB. Functionally, it handles electrical connections, mechanical support, signal transmission, and package size control. In other words, a glass substrate is not simply putting ordinary glass into a chip, but transforming a piece of specialty glass into a high-precision electronic component with hundreds of thousands or even millions of stable interconnection nodes. Why do AI chips need glass now? Advanced packaging is becoming larger and larger. AI accelerators, high-bandwidth memory, HBM, chiplets, and high-speed I/O need to be integrated into a single package system. As package area expands and wiring density increases, traditional organic substrates gradually face problems such as warpage, dimensional stability, fine-line processing, and high-frequency signal loss. Silicon interposers offer high interconnect density, but are limited by wafer size, processing cost, and the economics of large area. Manufacturing. Glass provides an alternative. First, better flatness and dimensional stability. Glass deforms less during high-temperature processing, helping reduce large package warpage and trace misalignment risks. Second, the coefficient of thermal expansion, CTE, can be tuned through glass formulation. By designing the material, glass can be made to more closely match the thermal expansion behavior of silicon chips or packaging structures, reducing interfacial stress during thermal cycling. Third, low dielectric loss and excellent insulation. This makes it more suitable for high-speed, high-frequency signal transmission, as well as scenarios such as AI, RF, and co-packaged optics, CPO. Fourth, panel-level manufacturing potential. Glass can be processed in larger panels than silicon wafers, theoretically offering a chance to lower the unit cost of large-size packaging. Intel has stated that glass substrates are expected to support higher interconnect density and improve flatness and pattern distortion in large area packages, with initial target applications including data centers, artificial intelligence, and high-performance graphics computing. However, glass substrates are not chosen because they conduct heat better than silicon. Their direct advantages are primarily anti-warpage, low loss, fine interconnects, and large area fabrication. The heat generated by chips still needs to be removed through thermal interface materials, vapor chambers, heat sinks, and liquid cooling systems. The real industry barrier isn't just drilling holes. The TGV may look like simply drilling holes in glass, but achieving mass production requires simultaneously addressing 6 areas: specialty glass substrate, control over glass composition, CT, dielectric properties, thickness variation, internal defects, and surface flatness is necessary. Microvia formation. Current mainstream approaches include laser drilling, laser-induced modification followed by wet etching, and photosensitive glass processes. Factors such as via diameter, aspect ratio, sidewall roughness, and microcracks all impact downstream yield. Via metallization. Glass itself is non-conductive. A seed layer must be deposited, followed by electroless copper plating or electroplating. High aspect ratio vias are prone to voids, plating breaks, insufficient adhesion, and thermal cycling failure. Redistribution layers and build-up. Fine copper traces, dielectric layers, and pads must be fabricated on the glass surface while controlling multi-layer alignment accuracy, singulation, and edge strengthening. Glass is brittle. Microcracks generated during cutting and handling can propagate in subsequent packaging and thermal cycling. Inspection and reliability. When a panel contains millions of vias, even a very low single via defect rate can significantly impact overall panel yield. Therefore, the core competitiveness of glass substrates does not lie in any single laser tool or plating chemistry, but in the full process yield formed by glass material, microvia processing, metallization, circuitry fabrication, inspection, and packaging verification. Semi's 2026 Glass Core Substrate Industry Report also identified TGV formation, metallization, build-up, singulation, defect inspection, reliability, and standardization as key issues for industrialization. Global competition. Leading players have formed a 3-tier industry structure. Currently, the global glass substrate industry features 3 main types of participants: chip and advanced packaging platform companies, specialized glass substrate manufacturers, and specialty glass material suppliers. Chip and advanced packaging platform. Intel took the lead in defining the technology roadmap. Intel is one of the early chip companies to systematically disclose a glass core substrate roadmap. In 2023, Intel announced R&D achievements on next-generation glass substrates for advanced packaging, planning to introduce them into products in the second half of this decade. Its core goal is to leverage glass's superior flatness, dimensional stability, and fine patterning capability to enable larger, higher interconnect density multi-chiplet packaging. Intel believes glass substrates can improve warpage and pattern distortion issues in large-size organic packages and support finer line/space and bump pitches, with initial target applications mainly covering data centers, AI, and high-performance computing. As an integrated device manufacturer spanning chip design, wafer fabrication, and advanced packaging, Intel's significance lies not only in developing glass materials, but also in its ability to perform system-level validation from chip architecture, packaging design, to substrate manufacturing. Specialized glass substrate manufacturers, Absolics, Samsung Electro-Mechanics, and DNP accelerating industrialization. Absolics, a glass substrate specialist under South Korea's SKC, is one of the professional manufacturers with relatively large industrialization investment globally. The company has built a commercialization plant in Georgia, USA, and received up to $75 million in direct funding under the U.S. CHIPS and Science Act. Its products are primarily aimed at advanced packaging for AI, HPC, and data centers, shortening interconnect distance between chips to improve signal transmission efficiency and reduce system power consumption. However, Absolics is still in the stages of fab construction, customer onboarding, and manufacturing process ramp-up, needing yield and reliability verification before reaching mature, large-scale stable supply. Samsung Electro-Mechanics, building on its FCBGA package substrate expertise, has identified glass core substrates as a key direction for next-generation high-end packaging. The company has produced glass packaging substrate samples on a pilot line at its Sejong plant in South Korea and is co-developing glass core substrates and glass interposers with AI and server customers. In 2025, Samsung Electro-Mechanics signed a memorandum of understanding with Sumitomo Chemical and its subsidiary Dongwoo Finechem to establish a joint venture for glass core materials, targeting mass production after 2027. Japan's DNP leverages its strengths in fine circuitry, lithography, and large area panel processing to develop both copper-filled and whole-wall metallized TGV glass core substrates. DNP has scaled its products to 510 mm x 515 mm panel size and aims to achieve related business sales targets in fiscal year 2027. That its advantages lie in fine metal traces, adhesion between glass and copper layers, and large panel processing capability. These companies represent the main midstream manufacturing routes for glass substrates globally, but none have yet entered a mature, large-scale deployment phase. Upstream specialty glass materials, AGC, NEG, and Corning hold the material foundation. Industrialization of glass substrates requires not only via and metallization processes, but also dedicated glass substrates tailored for advanced packaging. The AGC has developed a TGV glass substrate product lineup for semiconductor packaging, offering materials with different glass formulations, thicknesses, and CTEs, supporting both wafer and 510 mm x 515 mm panel formats. Its products can be used in chiplets, CPO, RF devices, and 3D integration. Nippon Electric Glass, NEG, is advancing both ordinary glass core and glass ceramic core routes. The company has developed two types of TGV glass core substrates suitable for laser-induced modification, etching, and CO2 laser processing, and has begun providing 515 mm x 510 mm large panel samples. Among them, the glass ceramic core material compatible with CO2 lasers is planned for volume production around 2028, aiming to reduce TGV processing costs and glass cracking risk. Corning has long-standing expertise in advanced packaging glass carriers, low total thickness variation glass wafers, and precision TGV glass. Corning currently focuses more on temporary bonding carriers, panel-level packaging carriers, and precision glass materials, rather than directly manufacturing complete glass core packaging substrates. Nevertheless, It remains a critical upstream player in the global glass substrate industry due to its capabilities in glass formulation, melting and forming, surface quality, and CTE control. In summary, the global glass substrate industry has formed a relatively clear corporate tier structure. Intel drives chip and packaging architecture applications. Absolics, Samsung Electro-Mechanics, and DMP advanced glass substrate manufacturing, and AGC, NEG, and Corning provide upstream glass materials and process platforms. However, the mass production timelines announced by these companies are not aligned. Semi's 2026 Glass Core Substrate Industry Report suggests that glass core substrates may first enter limited production for a few high-performance applications around 2028, with a projected market compound annual growth rate of 67.2% from 2028 to 2040. This indicates that glass substrates have considerable long-term growth potential. But 2026 remains a period of fab construction, sample verification, and process maturation. One cannot equate building a pilot line, starting to send out samples, and achieving volume production. Which links are Chinese companies breaking through? CCTV reports indicate that domestic industry clusters for electronic glass and advanced packaging have formed in cities such as Hefei, Bengbu, Xianyang, Chengdu, Wuhan, and Changsha, with the industrial chain extending from traditional display glass and cover glass toward TGV and glass-based advanced packaging. Based on public information from listed companies, domestic players can be divided into 4 categories: glass packaging substrates and TGV processing, upstream glass substrates, TGV laser equipment, and via metallization and electronic chemicals, glass packaging substrates and TGV processing, BOE, Woge Optoelectronics, Lens Technology, and Meidekai. In terms of direct industry chain involvement, BOE-A, Woge Optoelectronics, Lens Technology, and Meidekai are representative listed companies in China's glass substrate and TGV processing field. BOE-A, a panel-level glass packaging substrate platform company. BOE is one of the most systematically deployed enterprises in domestic glass packaging substrates. The company initiated glass substrate technology research in 2020, invested in building a wafer-level innovation platform compatible with glass and silicon in 2022, and further invested 993 million yuan in 2024 to construct a panel-level glass packaging substrate pilot line. By the first half of 2026, this pilot line had achieved fully automated equipment line-through, with a design capacity of 1,000 panels/month, and completed full process integration covering TGV drilling, deep via copper filling, build-up layers, and wiring. The company also completed sample development and delivery of large-size glass substrates with a 929 configuration totaling 20 layers, targeting glass core substrates required for AI computing chip advanced packaging. Some customers have passed concept verification and entered the technical testing phase. However, BOE has not yet achieved mass production or mass production revenue. IT still needs to further improve pilot line yield and complete long-term reliability certification with customers. Therefore, BOE's more accurate current positioning is a domestic leader in panel-level glass packaging substrate platforms. The full process flow has been established, but it remains in the customer testing and mass production validation stage. Woge Optoelectronics, a TGV and glass multi-layer interconnect technology platform, through entities such as Hubei Tongwei, Woge Optoelectronics is engaged in glass-based TGV via metallization, glass multilayer circuits, and packaging substrates, making it one of the domestic companies with relatively complete TGV full process capabilities. The company has built a glass-based TGV multilayer circuit board production line and is extending related technologies from micro-LED displays to optical modules, CPO, RF communications, and large computing power chip advanced packaging. However, company announcements indicate that its semiconductor-related products are still primarily in the stages of R&D verification, sample delivery verification, and joint customer development, without yet forming scaled industrial mass production. Related revenue accounts for a relatively low proportion, and some operating entities are still in a loss-making state. Therefore, Woge Optoelectronics cannot simply be described as having a production line at full capacity. Its true positioning should be a representative domestic company in TGV and glass multilayer interconnect technology, possessing a relatively complete process and production line foundation, but the advanced packaging business is still in yield ramp-up and customer verification. Lens Technology, extending its precision glass mass manufacturing capabilities to TGV. Lens Technology has long accumulated capabilities in precision glass processing, laser processing, chemical etching, coating, and automated manufacturing, and is now extending these technologies to TGV glass substrates. Its 2025 annual report listed TGV glass substrates as a key R&D project, planning to build a TGV pilot line that combines technological advancement with mass production feasibility, focusing on breakthroughs in high aspect ratio via formation, high-speed micro via filling, large size glass warpage control, and high-precision planarization. CCTV reports show that Lens Technology's TGV glass substrates are undergoing multiple rounds of sample delivery verification with domestic and overseas customers. And the company also plans to build approximately 30,000 square meters of dedicated glass substrate workshops and supporting production lines, expected to be operational by the end of 2026. Lens Technology's strengths lie in its precision glass manufacturing experience, automation equipment capability, and large-scale production management. But its TGV business is currently still in the stages of pilot trials, sample delivery, and production line construction. Its current positioning is an important potential leader in domestic TGV glass substrate mass manufacturing with strong industrialization capability. But mass production realization still awaits dedicated line commissioning and customer certification. Meidekai, glass carriers have shipped, but full TGV remains in the technology reserve phase. Meidekai has built process reserves in glass wafer precision processing, laser-induced modification, wet etching, PVD, electroplating, CMP, and RDL. However, a distinction must be made between semiconductor glass carriers and TGV glass substrates. The company currently supplies primarily non-drilled semiconductor glass substrates to customers that in 2025, sales revenue from these products accounted for about 2% of total revenue, still on a small scale. Although the company has developed TGV processes including through-glass vias, via metallization, CMP, and RDL wiring, these full TGV process products have not yet generated mass production revenue. Therefore, Meidekai's more accurate current positioning is that it has achieved semiconductor glass carrier shipments and possesses a full TGV process reserve, but TGV products have not yet entered volume production. In summary, no single absolute leader has emerged in China's direct glass substrate manufacturing segment. BOE leans toward a panel-level glass packaging substrate platform. Woge Optoelectronics toward TGV and glass multi-layer interconnects. Lens Technology toward precision glass processing and mass manufacturing, and Meidekai toward glass wafers and semiconductor. Microfabrication, Upstream glass substrates. Rainbow Display, Kibing Group, and Triumph Science and Technology are still mainly building technology reserves. The upstream glass substrate determines the CTE, dielectric properties, thickness uniformity, internal stress, and defect levels of the final product, forming the foundation for glass substrate industrialization. However, the technical requirements for display glass, cover glass, and chip packaging glass are not identical. Having display glass production capacity does not necessarily mean having the ability to mass-produce semiconductor packaging glass. Rainbow Display is an important player in high-generation display substrate glass in China, with experience in glass formulation, melting, forming, and large-size substrate manufacturing. However, the company's latest announcement clearly states that its products are still mainly used in LCD panels, and semiconductor packaging glass is still in the new application survey and R&D stage, with no products entering semiconductor packaging-related testing. Therefore, Rainbow Display should be positioned as a display glass leader and a potential packaging glass material platform, rather than a semiconductor glass substrate supplier already delivering to TGV lines in volume. Kibing Group has a strong mass manufacturing foundation in float glass, electronic glass, and high-performance glass. But the company has explicitly stated that it has not yet invested in building a mass production line for chip packaging glass projects, and there is no related mass production business or corresponding revenue. Thus, Kibing Group is more appropriately viewed as an electronic glass material platform and a potential technology reserve company. Industrialization of chip packaging glass still faces significant uncertainty. Triumph Science and Technology has technical expertise in UTG, ultra-thin glass, electronic glass, and specialty glass. But the company also clearly cautions that TGV technology is still in the early R&D stage and has not achieved commercial mass production or revenue. Hence, Triumph Science and Technology's current positioning is that it has a specialty glass and TGV technology foundation, but remains a considerable distance from commercial mass production. These three companies have strong glass material foundations and potential extension capabilities, but at this stage they cannot be equated with companies like BOE, Woge Optoelectronics, and Lens Technology that have already entered full process verification or production line construction phases. TGV equipment, Dier Laser, Hans Laser, and Delong Laser. TGV microvia processing typically requires femtosecond lasers, picosecond lasers, or laser-induced modification, plus wet etching equipment. The equipment segment often sees orders before large-scale substrate mass production, and thus may be the first to benefit from pilot line and trial line construction. Dier Laser has already shipped wafer-level and panel-level glass substrate via drilling equipment, achieving coverage of two types of TGV laser tools, making it one of the domestic companies with relatively clear progress in TGV equipment industrialization. However, the company also notes that the glass substrate industry is still dominated by pilot lines and trial lines, and equipment shipments do not indicate that downstream customers have entered large-scale mass production. Hans Laser has launched wafer-level and panel-level TGV equipment, compatible with wafers up to 300 millimeters and larger glass panels, capable of processing through vias, blind vias, and shaped holes. The company has strong vertical integration capabilities in lasers, optical systems, motion control, and automation integration, but has not yet separately disclosed the revenue scale and major customer structure of its TGV equipment. Delong Laser has deployed wafer-level and panel-level TGV equipment, as well as advanced packaging tools for glass cutting, grooving, splitting, and laser debonding. Its strength lies in the synergy between ultra-fast lasers and complete machines, but the actual batch delivery and revenue contribution of TGV equipment still need further observation. Therefore, the criterion for evaluating the domestic equipment segment should not simply be whether they have TGV equipment, but also include equipment acceptance, repeat purchases, line utilization rates, and order sustainability, metallization and electronic chemicals. Skychem Technology is progressing faster. In industrialization, glass itself is non-conductive. After TGV processing, a seed layer must be formed, followed by electroless copper deposition and electroplating to achieve via conduction. The high aspect ratio vias are prone to voids, gaps, uneven plating, and poor adhesion, so electroplating additives directly impact overall panel yield and reliability. Skychem Technology has deployed advanced packaging electroplating additives for TGV, TSV, RDL, and bumping. Company communications indicate that its TGV electroplating additives have achieved batch shipments and are gradually ramping up, while cooperating with some leading customers on mass production plans. This suggests that Skychem Technology has transitioned from technology development and customer verification into a stage of commercial supply. However, its ultimate revenue scale still depends on the expansion and mass production progress of downstream TGV lines. Eisen Semiconductor has similarly deployed TGV high-speed copper plating additives, but is still in the customer testing and verification stage. Thus, in the glass substrate electronic chemicals segment, Skychem Technology currently holds a relatively more advanced industrialization status, while Eisen remains focused on product verification. Overall, China's glass substrate industry has covered major links including glass materials, TGV processing, metallization, circuit fabrication, laser equipment, and electronic chemicals. However, significant differences in industrialization stages remain among domestic companies. BOE, Woge Optoelectronics, and Lens Technology are in the stages of full process integration, sample verification, or dedicated production line construction. Meidekai has achieved shipments of non-drilled glass carriers. Dier Laser and Skychem Technology have realized certain product deliveries in equipment and chemicals, respectively, while Rainbow Display, Kibing Group, and Triumph Science and Technology still focus mainly on material platforms and technology reserves. Therefore, when identifying domestic glass substrate leaders, one cannot look merely at whether a company has a glass substrate concept. Instead, one must focus on whether the full process is integrated, whether customer certification is completed, whether yield can be stabilized, whether capacity has truly been released, and whether the related business can generate sustainable revenue. How will glass substrates ramp up in volume? Judging from currently available progress, glass substrates are likely to develop in 3 stages. 2026-2027. Equipment introduction and process verification. This stage will first see increased demand. For laser equipment, wet processing tools, electroplating equipment, inspection tools, glass substrates, and electronic chemicals, there will be many corporate announcements, but most revenue will still likely come from pilot lines, samples, and small batch orders. 2028-2030. Limited adoption and high-value scenarios. Products with high requirements for dimensional stability and signal integrity, such as AI accelerators, HPC, chiplets, CPO, RF, and MEMS, are expected to be the first to adopt glass core substrates. Due to high initial costs, mainstream consumer electronics are unlikely to be the earliest large-scale application. After 2030, dependent on yield, cost, and industry standards. Whether glass substrates can expand from high-end packaging to broader applications will mainly depend on four variables. First, whether TGV and metallization yields can stabilize. Second, whether panel-level manufacturing can truly reduce costs. Third, whether upstream and downstream materials and equipment can form a standardized supply chain. And fourth, whether leading chip customers complete long-term reliability certification. On the policy side, advanced packaging, packaging substrates, electronic glass, and key IC materials have been included in nationally encouraged industrial directions, providing long-term support for industry chain R&D and capacity building. However, policy support cannot replace product certification, nor can it guarantee that all companies entering the glass substrate concept will ultimately succeed. How to judge whether a company truly benefits. When observing the glass substrate industry, one cannot only look at whether a company announces a TGV layout. Rather, 5 indicators should be tracked in sequence. First, whether it has obtained formal certification from leading customers. Sampling is only the starting point. The certification cycle and reliability data are more important. Second, whether it possesses a complete process chain. Having only drilling capability differs greatly in commercial value from having integrated capabilities in metallization, RDL, singulation, inspection, and packaging collaboration. Third, whether yield and stable production capacity are disclosed. There is a clear gap between lab samples, small batch pilot production, and volume manufacturing. Fourth, whether identifiable revenue has been generated. Point 1 should distinguish between R&D investment, equipment orders, sample revenue, and genuine mass production revenue. Fifth, whether it has sustainable customer and technology barriers. The ultimate winners are likely not the companies with the most eye-catching single-step parameters, but those that can integrate glass material, processing technology, equipment, and customer validation. Conclusion: glass substrates are not a suddenly emerging new concept. They have drawn attention because AI chips are driving continuous increases in package area, interconnect density, and signal speed, while traditional organic substrates and silicon interposers each face new boundaries. From a technical logic standpoint, glass substrates hold real value. From an industrialization progress perspective, they are still in a transitional phase from pilot trials and sampling to limited production. From a market space viewpoint, the long-term potential is enormous, but the superglass Trillion-Yuan Track cannot be directly equated with the near-term revenue of semiconductor glass substrates. In 2026, what is truly worth watching is not which company is the first to shout mass production, but who can first overcome the 3 hurdles of customer certification, full process, yield, and mass manufacturing cost. That is the key to glass substrates moving from a hot concept to the next generation AI packaging foundation.